Okay, good morning. So I will share.
Good morning, sir.
So I think Aniruddhan has not, maybe he's having difficulty in getting connection. Okay, let's proceed. I will share the screen. Okay, the last class we had seen a proof of this. We have proved this result. If YIs are IID, that is independent, identically distributed, one-dimensional, continuous random variables, and suppose F is their PDF, common PDF, then the PDF of the corresponding order statistics is given by n factorial times that F evaluated at Y1, Y2, Yn, etc. If the Yi's are strictly in increasing order, Yi or Y1 strictly less than Y2, etc., etc., and zero outside of that region. I think this region we had denoted by G or Gn or something like that. Anyway, I don't remember the exact thing we gave. And also we had seen this corollary. That is, in case the IIDs happen to be having a uniform distribution on the interval 0 to t, then the order statistics that the value of the order that PDF of the order statistics is hy1 by 2 yn equal to n factorial multiplied with 1 over t to the power n. 1 over t, recall, is the uniform density over 0 to t. That is the PDF of the uniform distribution on the interval 0 to t. So that raised to the power n. So if all the Yi's are strictly increasing order and they are strictly between 0 and t, and it is elsewhere, the PDF is 0. So it is this set where the order statistics will take value. Probably we had denoted this by G, N, T or something like that. So now we will see the connection between Poisson process and order statistics, and for this corollary will be used. And of course, that the proposition ahead, which we had stated earlier, will play a role also. Okay. So all these things are, I think you might have copied it down already because it was done last meeting. Okay. So now we look at Poisson process and order statistics. So the theorem says if n is a time homogeneous Poisson process with arrival rate lambda and wi's, I running over 1, 2, 3, etc. are the corresponding successive arrival times. So then what happens? And also you fix a t strictly positive and also an n. N is also fixed, an integer, positive integer n is fixed, and a positive real number t is fixed. So we are going to consider the orders or wi's taking values in the interval 0 to t, the probability of the wi's given exactly n events or n arrivals are there during 0 to t. Yeah, please note it down if you want to. Okay. Then the result says the conditional probability density function of W1, W2, Wn given nt equal to n. So that is given by, so the conditional density at S1, S2, Sn given Nt equal to n. So this is the PDF, conditional PDF is n factorial times 1 over t to the power n if these SIs are in strictly increasing order, that is 0 less than S1, strictly less than S2, less than etc., less than Sn and less than t. And this conditional density is 0 outside of this region. So the conditional distribution of W1, W2, Wn given Nt equal to n, it is the same as that of the order statistics of n independent identically distributed random variables, with each of them having a uniform distribution over 0 to t. Note that these Wi's are in strictly increasing order with probability 1. Probability of W1 strictly less than W2, strictly less than Wn is 1. Of course, if you are also given the information that there are exactly n arrivals or n events have happened in the interval 0 to t, so this means exactly n events or n arrivals have taken place in the interval 0 to t. So given this information and together with all these Wi's are all strictly increasing, we know that this, with this information and this random variable, this n-dimensional random variable will have to take value in this set with probability 1. Probability of that random variable taking values in this set is 1. And the corresponding conditional density function has this form, which is the same thing as order statistics. Okay. So please note it down if you want to. All right. So denote by G sub nt is the set of all n tuples, that is S1, S2, Sn, such that 0 is strictly less than S1, which is strictly less than S2, and so on, strictly less than Sn, and that Sn is also strictly less than t. So this is the collection of all points in Rn such that the coordinates are all between 0 and t. And not only that, they are in increasing order, strictly increasing order. So as we had done in our earlier discussion, we take a rectangle, n-dimensional rectangle, completely contained in this. So n-dimensional rectangle would be this product of one-dimensional intervals. So let this product I going from 1 to n, ai, bi, denote this rectangle a1, b1 cross a2, b2 cross etc. an, bn. And also we stipulate that this rectangle should be completely in G and T. Note it down. So as we had done earlier, because of all this rectangle is contained in GNT and GNT is of this form, just like we did in that, you take the 2-dimension and draw an example of a rectangle which is contained in that kind of a set. So that kind of argument will easily give you that you have this sequence of inequalities, 0 less than or equal to A1, strictly less than B1, which could be less than or equal to A2, etc., 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 and finally the Bn less than T. So we proceed as we use the result which we had seen in that earlier notes, Poisson process 2, I think there it is called proposition 4, which gives you the probability density function for any n-dimensional, this W1, W1, W2, Wn, Wn. But here you need to take the n plus 1th dimension also, because this Wn plus 1 will be bigger than T. Because we know that Nt equal to N. So only up to this guy, all these guys are going to be inside 0 to T, and this one will be outside. So as we had done before, verify that. So that is a long sequence of equations. But fairly elementary. Okay. So probability W1, W2, Wn belonging to that rectangle, product I going from 1 to N, Ai, Bi. So that probability given Nt equal to N. So by definition of conditional probability, this is going to be probability of this event and this event divided by probability Nt equal to N. So that what is going to be the denominator we have written here, and what is going to be in the numerator is this. So A1, I mean W1 would be between A1 and B1, etc., etc. Wn would be between An and Bn, and we also know that Nt equal to N. So Nt equal to N means Wn plus 1 has to be strictly bigger than T. Because remember that Nt is the number of events or number of arrivals during the time 0 to T, T included. T is closed at the closed Nt. Consequently, this probability can be written as up to Wn being in A and Bn, you retain the same thing, and Wn plus 1 great, strictly bigger than T. So this W1, W2, Wn, comma Wn plus 1 is taking value in corresponding to this event A1, B1 cross A2, B2 cross An, Bn cross T, T to infinity. Okay, please carefully note this here. Why this is equal to this? So it takes value in that rectangle, which I just now mentioned. That is this guy times T to infinity. It is to be a rectangle in the n plus 1 dimensional space. And in that case, we know the PDF of conditional PDF of W1, W2, Wn, Wn plus 1, not conditional. It is a PDF of W1, W2, Wn, Wn plus 1. And that is given by this. For any S1, S2, Sn taking value in the rectangle which is given by this n-dimensional rectangle times t to infinity. Okay. So this step is a crucial step, this equation. Okay. Now, in this lambda n plus 1 to lambda to the power n plus 1, just keep one lambda here and bring the lambda to the power n outside. Then you will have lambda times e to the power minus lambda s plus Sn plus 1 dsn plus 1. So that interval, this integral can be easily evaluated, and that is precisely e to the power minus lambda t. You are integrating with respect to the variable s sub n plus 1. So you are evaluating this integral after taking lambda power n outside. So what remains there is precisely the exponential density with parameter lambda. And that you can easily evaluate over an interval of the type t to infinity. And that precisely is this quantity. And now note that this one does not depend on S1, S2, Sn. So that also gets pulled out. And you know the expression for P, this probability nt equal to n, you know nt has a Poisson distribution with parameter lambda t. So you know this, the value, that is precisely lambda t to the power n multiplied with e to the power minus lambda t divided by n factorial, and that n factorial has come in the numerator. So here these exponential terms, they cancel out, and the lambda n here cancels out with the lambda power n here, and what remains here is just n factorial divided by t to the power n. And that you bring it inside the thing. And so you have expressed now the conditional probability, that is probability W1, W2, Wn taking value in this rectangle given nt equal to n is an integral over this set of n factorial divided by t to the power n ds1 to ds2 ds1. I mean dsn to ds2 ds1. Please carefully go through this, note it down. Don't make any transcription error. And also check that I have not made any error. So what we have succeeded in doing is, if we take any arbitrary rectangle, let's say product I going from 1 to n, ai, bi, which is completely contained, any open rectangle in G and T, then the probability of this n-dimensional random variable taking values in that rectangle given nt equal to n is given by integral over this, precisely this rectangle of this function n factorial divided by t to the power n, of course, ds and ds2 ds. So this gives the expression for any rectangle contained in that G and T. So therefore, this has to be the PDF. Of course, measure theoretic justification can be given. That is, such open rectangles generate the so-called Borel sigma algebra of G and T. So if you are not familiar with measure theory, you can assume that proving this kind of an expression for every open rectangle inside that thing which is bound to be the range of that random variable, from that you can conclude that this function which occurs here is the probability density function. So the proof of the result is now complete. Okay, please again take a look. Okay. One comment, after typing out this proof with the notes and all that, I realized that there can be slightly shorter proof, more, somewhat similar to how we found the probability density function of W1, W2, Wn, similar to that. So what we are going to do is this thing, instead of writing it this way, we are going to do it similar to what we have done in the when we found the density of W1, Wn. Okay. So I have mentioning that as a remark. So for this, you need to use the independent increment property, and in that Poisson process 2, in that notes, the very first theorem. That is where we derived the Poisson process. In that, I think there is an equation which gives you the distribution of NT, which is called, I think, asterisk or something. Okay. So what we are going to do is we will look at this probability. Probability A1 less than W1 less than or equal to B1, etc., etc. AN less than Wn less than or equal to Bn, and Nt equal to. Okay. So what this means is, up to time point A1, no arrivals. So the probability, this event, the event which is here, is same thing as NA1 equal to 0, and the first arrival is between A1 and B1. So NB1 minus NA1, that gives you the number of arrivals in the interval A1, B1 is exactly 1. and from A2 to B1, there is again no arrival, etc., etc. And NAN minus NB1, Bn minus 1 is also 0. And Wn is in ANBN. But we are also given that NT is equal to N and Bn is less than or equal to T. So therefore, here there can be exactly one event. So NB1 minus NA1 equal to 1. In the earlier derivation of W1, Wn, which we did quite a few last week or something, from this alone, we cannot conclude it is this. We have to write here greater than or equal to 1. If you go back to the notes, you will see that. But since we are given this information together with NT equal to N, enables you to conclude that NBN minus NA1 is equal to 1. And you know that since NT equal to capital NT equal to N and the Nth event has arrived before Bn, between Bn and T there cannot be any arrivals. Therefore, NT minus NBN equal to 0. Okay, this is just similar to the kind of argument we had used in the unconditional, that is the density of PDF of W1, W2, Wn in that derivation. You can compare with that. But here, in addition to this information, we also have this information. So these two information together is the same as NB1 minus NAN is equal to 1 and also NP minus NBN is equal to 0. Yeah. So that is how we arrive at this equation. And in this, to derive this, you use the independent increment property. So this is probability NA1 equal to 0, probability NB1 minus NA1 equal to 1, multiplied with the probability NA2 minus NB1 equal to 0, etc., etc., and probability NBN minus NAN equal to 1, this thing, and probability NT minus NBN equal to 0.
Sir?
Yeah.
Rightmost portion is not visible.
Yeah. But that you know, that's why.
Yeah.
Probability of this event. So that is probability NT minus NBN equal to 0. Okay. And since you know the exact distribution of this, NA1 has the Poisson distribution with the parameter lambda A1. And that probability that random variable equal to 0. And that precisely is e to the power minus lambda A1. And here you know that this random variable NB1 minus NA1 has the Poisson distribution with the parameter lambda times B1 minus A1. And that takes the value 1. And that probability is precisely lambda times B1 minus A1 multiplied with e to the power minus lambda B1 minus A1. And so on. So alternately, it will come this kind of a term followed by this term corresponding to exactly one event and followed by corresponding to 0 event in that interval and so on. And here you have this expression, this one lambda times Bn minus An multiplied with e to the power minus lambda Bn minus An. That corresponds to probability Nbn minus Na1 equal to 1. And the last term, this is precisely that equal to 0, that is e to the power minus lambda times T minus Bn. So that is not coming out clearly here. But anyway, once you get the hang of it, you know how to do it. And anyway, in a few days, you will get the notes. it will be uploaded. To sort of completely write down this correctly is an exercise for you now. To check that whether you are understanding the Poisson process. So now note that e to the power minus lambda a will cancel with e to the power minus lambda times minus a1, that will get cancelled and so on. And finally, what might remain in the exponential term is just e to the power minus lambda t. All the others would have cancelled. And then the lambda times b1 minus a1, lambda times b2 minus a2, lambda times bn minus an, all those things will remain. And there are n such, so all the lambda n's you collect together, take it outside, and b1 minus a1 can be written as integral a1 to b1 of ds1 and so on. bn minus an can be written as integral dsn. So you get this expression. This we denote as by double dagger. So what we have on the right side of double dagger, comparing with here, so that thing is precisely this n-dimensional integral with that, what is it? E to the power minus lambda t, lambda power n. Yeah. So this portion, lambda to the power n times e to the power minus lambda t times that integral. So what you will have here is 1 divided by probability nt equal to n times this thing. So once you get the double dagger, the single dagger follows easily. So that is another way of giving the proof of this result. Check this because this I had not seen earlier. So it is just, I think it is perhaps a slightly simpler proof. So that sort of finishes the proof of the theorem. Now, next we will start with one example, but we will take it up more carefully the next class. So please note it down. If you want me to go back to any of the other slides, also you can do that.
No, sir.
Okay, thanks. So this is an example. So suppose that passengers arrive at a train station. You can even consider it airport or bus station or anything, in accordance with the time homogeneous Poisson process. Let's say n with arrival rate lambda greater than 0. Suppose the departure time of the train is at capital T, which is fixed. This capital T is fixed beforehand, it is known. So passengers would be arriving, I mean, before time capital T. Of course, the people who come after time t, they just miss the train. That's it. So we want to find the expected sum of waiting times of customers arriving during 0 to t, capital T. 0 is something like they know that by this thing, if let's say the train departs at 11 o'clock in the morning, generally people start arriving from, let's say, 9 o'clock. At least the airport and all, we know that one has to report now 2 hours in advance and so on. So you can say that something like that. So expected sum of waiting times of customers. So a customer, a typical customer, if he comes at, let us say, at time yes, he will have to wait for time t minus s units of time. So what is the average waiting time for all the guys who might be coming during this interval 0 to t? So this kind of quantity computing this thing, you can give some kind of an idea about what amount of what type of space at the station may be needed. Let's say waiting room or something like that. So to plan such things, this kind of quantities will be useful. One can have some idea about, let's say, each person may may need certain space. You cannot be pack them like very tightly the waiting room. There might be sufficient space between 2 individuals. And also the facilities available can also depend on that. You may have to install so many water taps and things like that. So plan all these things. It cannot be too big because then there will be a lot of space will may be wasted, and that also can be expensive, especially if it is in some prime location in a city. Okay. So we need to find, so the train departs, at time capital T. Since these passengers come according to this process, Poisson process, the total number of people who would have arrived by that time is capital N, I evaluated at T. That's a random variable. But then somebody who arrives at, let's say, time S, which is strictly less than T, will have to wait for T minus S units of time. Consequently, let's say the ith customer arrives at time Wi, and let's say Wi is less than T. So that person will have to wait for time T minus Wi. So these Wi's are the waiting arrival times of customers, with the Wi denoting the arrival time of ith customer. So we have to find this. To get hold of this, what we are going to do is, we will write this as conditional expectation of this quantity given nt equal to n. So the whole thing multiplied with probability nt equal to n and sum over little n. So we are going to find the expectation. We are going to write this as expectation that we will see next class. Yeah, that we will see next class. So we are going to write this as summation little n going from n to infinity, because this nt we don't know the exact value, it is random. We only know that nt takes value according to the Poisson distribution with parameter lambda times capital T. So summation little n going from 1 to infinity, conditional expectation of that is this quantity given nt equal to n multiplied with probability nt equal to n. You know that expression. I mean, in the sense, you know that formula. And when you take that conditional expectation that this quantity given nt equal to n, so for that you have our result. This will we'll make use of this today's result. This we know. For each little n, we know this PDF. Yeah. And that will involve IID uniform random variables. Yeah. So to compute the required quantity for any fixed little n, any integer, u1, u2, un denote independent identically distributed random variables, each having a uniform distribution over the interval 0 to capital T. So for each n, we will have this kind of a sequence. This is an important thing. We will also assume, so for each n you have this, so we can see, even say that u1, u2, u1, that is a sequence of uniform random variables. So that ui's which are uniformly distributed, not only can they be taken to be independent of each other, but that can also be independent of the Poisson process NT. The UIs can be taken to be independent of this process. How this can be achieved? I mean, if one doesn't know measure theory, it may look somewhat mysterious. I mean, you can, those who don't know measure theory can take it on faith. So this can be justified by the basic probability space. You expand that as a suitable product space. So we won't go into this argument. We will just be sort of satisfied that this comment can be justified using measure theory. And we will stop here for the day. So if you have any comment or any question, or you want me to go back to any of the slides, I'll be happy to do it. Okay. So we'll stop sharing and end the session.
Thank you, sir.
Okay. Take care. Stay safe. Yeah. Okay.